And recording in progress. And when I made this presentation, I later realized that advanced chapel is a very, very vague and broad notion. And the features that I would pick when I am introduced, or when I have to introduce advanced chapel, are as much a reflection of me as they are a reflection of the language. Um, kind of like the ink blot test, really. And I picked features that I thought would be useful for the more advanced tutorials later today, but that doesn't mean that that's all there is to advanced chapel. And in fact, so much advanced material exists that you cannot cover it in the span of 30 minutes in one presentation. And as a non-exhaustive list, before I proceed, of things that I haven't covered, but will be covered or is covered elsewhere, is here. So I would consider performance work a relatively advanced topic. Engin will be giving a demo on performance analysis later today. And Michael Ferguson has kindly written an introduction to optimizing Chapel programs. And so I will provide QR codes that link to these resources in the next slide. So if you're interested in any of them, just hold on for a second. Also, advanced parallel programming techniques. I'm not sure. So Shreyas has already covered parallel loops, which in Chapel is much of how you use parallelism, in my opinion. And if you want to go deeper or lower level, as I mentioned in the introduction or yesterday, then days 11 and 12 of Advent of Code cover task spawning and synchronization using atomics and sinks. And beyond that, I think for parallel programming, the algorithms matter much more than do the building blocks of the language. So if you have these pieces, I feel fairly confident that you can write advanced parallel programs. And another kind of advanced or niche bit is interfacing with various other languages like C, C++, Fortran, Python. And we have a variety of blog posts and announcements that cover these things in much more depth than I could, and are also potentially more relevant to what you're trying to do. So one article article series actually is Scott Bachman's series on using NetCDF from Chapel. Brandon, who kindly started us off today, and Michelle have written a blog post in collaboration with Seaworthy that cover interoperable with Fortran. And the Python module, which is shipped with Chapel as of release 2.4, can be used to create and execute Python code. So I've talked for a while, and here are some QR codes that link to these various resources if you desire to learn more. I will hover on the slide for a little bit of time, these slides will be public as well. So actually, maybe I won't spend too much more time, but these are all references to the other material that I won't be covering today, but might be considered advanced and might be of use to you. So that leads me to what is included in the slide deck. And as I was thinking about what we'll be presenting, I realized that many of the lower level features that we use under the hood rely on deeper specifics of the language that aren't really common with other languages. And it's true both about how they're implemented and at times with how they're used. So like not just on how they're built, but also how you have to use them. And in some cases, this can mean that if an error message is weird, knowing what causes the error message to be weird is helpful. And in others, just knowing that this feature exists is kind of required to write code. And I'm being vague, but I'll go into more detail momentarily. And so what this boiled down to is actually a lot of type system and compiler features in Chapel. And effectively, that's what this talk will be about. So the big thing really is Chapel's compile time generic mechanism. So many of Chapel's features are written using generic code. So yesterday we saw distributions. We probably heard mentions of serializers and iterators in the I/O and parallel loop demos, respectively. And at the surface level, these generics were designed to be familiar to people coming from Python. So you can write code where you're not annotating your types. And then when you do add types to your program, you can just add them later and do it partially, like not even everywhere. And functions can decide what to do based on the types of their arguments. So they can do like, if the argument is a string, do this, else do that, which is something you do in Python fairly often. And in Python, this is achieved using dynamic typing. So at runtime, you will query the arguments types and make a decision about what to do. And type annotations in pure Python, last I checked, don't do anything at all. And they can be added later, of course, because they're not required because they don't do anything. But Chapel differs from Python in that it is actually a statically typed language, and you cannot just decide or query types at runtime this way. You actually want to generate an executable and compile time code and all that. And so even though generics look similar to what Python might be doing, they actually behave differently in practice. So to kick us off, consider this basic function foo, which just sums two numbers. This function takes two arguments, x and y, and we've omitted their types. And we cannot just compile foo by looking at this definition because we don't know the types of the arguments, so we don't know what to compile it to. And in fact, the types of the arguments are provided from when this function is called. So for each two arguments that you give to it, we produce a copy of the function that has the corresponding types. Or, if you, obviously we don't duplicate it if there's the same thing. So if you pass two ints in two separate calls, there will be one instance. But if you consider these two calls, foo 1.0 and 2, which is a call with real and int, we will produce a function foo with real and int. And then if we separately call the function with 1i and 1.0, which is an imaginary number and a real number, we will produce foo with x imaginary and y real. And this creates two instantiations. And yes, so these copies of the function that have particular types assigned to them are called instantiations. And they are each resolved separately, so they can behave quite differently. And we talked about conditions on argument types, and the way that those work is also compile time based. So since, as we mentioned, each instantiation of a function gets its own copy of the function, basically, including its body, then a function like foo with a conditional like this one on the left can be copied for any number of arguments. And so for copies where the argument is a string, this condition is automatically simplified to true. And then, because we know the condition is true at compile time, it gets reduced to the body of the then branch. Meanwhile, in copies of the function where the condition is known to be false at compile time, we reduce it to bar. And so at compile time, you can make decisions about types and build more specialized versions of your functions. And a little note about that, actually. So like I mentioned, some things are simplified at compile time, and this proceeds in a relatively fixed order, which is left to right, top to bottom. Arguments to functions get resolved first. And this actually lets you do things like return early and eliminate dead code that wouldn't run. So write code that wouldn't compile in some cases, but doesn't need to compile because something else works. As a concrete example, I want to write a function called myHash, which, if possible, calls a hash method on its argument x. But if x doesn't have a hash method, which can be possible if, say, you wrote your own type or something like that, then this function just returns 0. Also, if x is an integer, it doesn't need to call the hash method and can just return x. So this is the uninstantiated version of myHash, which I've indicated by graying out all of its body. And I'll be highlighting parts of this body as they are resolved, roughly in the order that the compiler will visit them. So initially, we check if the type is an integer and return x if it is an integer. Then we use a reflection library to check if the hash method exists on x. And if it doesn't, we return 0. And otherwise, we return x.hash. So if I instantiate, if I call myHash with an argument of type some type, then the first thing that happens is we create a copy of this function where x has this some type. And then we go through the statements in this function and resolve them one by one. So in this case, we first compare some type to int, because previously that was x dot type is equal to int. Well, some type is not an integer, so we get false, and some because I assume some type is some kind of record or class, like Jade mentioned in the previous tutorials. And since we know this condition is false, this statement basically just gets removed. And then we move on to the next statement, which is the condition, and we try to resolve x dot hash on some type. And x here is the variable of type some type. I pretend in this case that the hash method does not exist. So this returns to true because not false is true. And since this condition is true, we replace it with its body and say, hey, no hash method, return default value. And now all the code below this return is considered dead, so it's also removed by the compiler. And so from the original instantiation, what we get is a myhash function that just returns 0. And this is actually quite a powerful technique. And one interesting application of this that I've seen is a library by Luca Ferranti called forward mode auto-differentiation, or forward mode AD. So the fact is, as we've seen, each instantiation of a generic function is resolved independently. And we can actually use operator overloading or function overloading to change what calls are made from the function's body. So Luca's library here, what it does is rely on this to provide different overloads for a special kind of number-like thing called a dual number, which you can roughly think of as carrying a value and an approximation of a derivative. And there are certain rules to how these numbers are added and multiplied. They're slightly different to regular plus and minus and multiplication. Forward mode AD basically provides these numbers and overloads of these functions here in the bottomish middle, in the bottom middle. It provides overloads of functions using these numbers, the usual functions like sine, exponentiation, logarithm, and stuff like that. And when you write a generic function, or you write a generic function using these things, and then you can call it with a real number, and it just gets instantiated normally. So these calls to exponentiation, sine, and log turn into calls to the equivalent functions in the Chapel standard library, which operate on real numbers. But for instances with dual numbers, you actually end up calling the forward mode AD overloads of these functions. And these overloads properly compute the derivative using the dual number thing. So in effect, you get a normal instance of the function, and you get an instance of the function that computes both the value and the derivative. And in this way, you have, for free, a function that does the regular thing without any overhead, and also a different version of the function that has a derivative for you to be able to use. So far, we've seen that argument types can influence formal types when calling a function. But in fact, the compiler also supports having functions whose formal types depend on the types of preceding formals. So that might not be very clear, but if we look at foo matching here, we can have a function that accepts 3 arguments of exactly the same type. So for this, I accept x as a fully generic argument, y as a typed argument whose type is x dot type, and then z whose type is y dot type. It could have been x dot type, but just for instructive purposes made it y dot type. And so because there's this dependency, notionally you can think of type expressions and formals being resolved left to right as the call is resolved. So take, for instance, this foo matching call with 1, 2, 3, which ought to resolve. And we'll start with a fully generic instance of the signature. So the first thing that happens is that the first argument, x, is instantiated with a type of 1, which is int. At this point, we can also replace x.type with int. Following this, we pass in 2, and yes, 2 is an integer, so y of int passes. And now we also know that y.type is an int, and we can replace it in the type of z. And then finally, we pass in the 3 and yes, 3 is also an integer, so we end up with a matching function signature with types int, int, and int assigned to x, y, and z. And you don't have to have these type expressions be exactly matching. So you can build other types using or referring to previous types. So in this case, I've adjusted foo matching to take X and then Y, which is a tuple of X's type, and then anything else. That's the question mark here. So this is called as follows. So you have an integer and then a tuple of integer, integer, string. And again, we'll walk through how this is resolved. So foo matching here, we'll first have X instantiated with int because the first argument is an integer. And at this point, we'll replace x.type with integers in the body. So you get Y int, but still question mark there because we haven't passed in the second actual or second argument. And then once we pass in and check that the second argument matches, which is the tuple 2, 3, hello, we'll find out that this last tuple component that we haven't known yet is a string. And the final function signature is X of int, Y int string. And finally, you don't actually have to use .type to reference preceding formal information. You can also use type queries, which let you put almost like a variable placeholder where a number normally would go or a type would normally go. So here, int 8 is normally written int 8, but you can put a question mark W there to store the width of the integer X into W. And the same is true for types. So if you had, we'll see that on the next slide, actually. In this case, however, what I'm doing is taking an argument X, which is an arbitrary length integer, and exactly as many bytes as we need to make up X by reference. So in this case, if X is a 16-bit integer, we will accept two 8-bit arguments using variadic formals by reference. So as an example of how I might call this, and what I haven't shown you the body of this function, just not to pollute the slide, but I'm imagining that each one of the B's will get populated with the corresponding byte in X. So here I declare 2 bytes and pass in the hexadecimal number 2025 as an int16, 2 ints and bytes, and I also pass in the 2 bytes by variadic arguments. So if I passed in 3 or 1, it actually would not compile because this formal constraint says that X accepts that these B's accept as many bytes as X is Y divided by 8. And we'll step through this. So as we've seen before, we'll start with a generic signature. X is any integer width, or X is an int of any width, and then B's is a variadic formal with exactly as many as W over 8 arguments. When we pass in int 16, we basically replace W with 16 everywhere that it occurs. So in this case, W over 8 becomes 16 over 8, which is the same as 2. In practice, we expand the variadic formal to accept exactly 2 extra byte arguments, B as 0 and B as 1. And these will be the ones that B0 and B1 get passed to. And like I mentioned, you don't have to just query the width of integers. You can also query types. One famous example is querying the type of an array element. So array and element here is a function that takes an array and also an element of the same type as the array contains. In this case, I query the type of the array element using a question mark T, and then also accept another element of this type. And you might be thinking, well, wow, why do I need this? Well, the fact of the matter is that the standard library makes tons of uses of these. And if you're even reading the documentation for these procedures generated by ChapelDocs, say, on the website, you will encounter type queries and generics and things like that. A cursory examination of the standard library has yielded these examples. So the set library, union, intersection, pretty much every operator is constrained on sets of exactly the same type. So when you have or and, which is union and intersection, you will actually accept a set, and then the library queries the type of the set elements, and then enforces that the right-hand set has the same type of elements as the left-hand set. The array type query pattern that we just saw in the previous slide is used in the random module to fill arrays with random elements. In this case, it takes an array by reference, and then a minimum and maximum element of the same type as the array contains. Though this is documentation only, Comparators for sort modules are expected to have a signature in which two types match. And this is the very first example we saw, basically. And type queries and these type references or references to preceding formals are also used in the serializers API, which Ben will be covering later today. So in particular, this helper start record that I pulled from the documentation and many others contain a reference to this.type. So in this case, this is also a formal, just usually implicitly given to the method. And also, the serialized and deserialized methods are generic over the serializers and deserializers that are given to them, and that uses type queries. I think the API was intended to do a bit more with it than just query it, but in practice today, I think it just just uses the type query there. So you can scan this QR code here to get a link to the program, which gives you the time of Ben's demo, and that will be later today. Another thing I wanted to quickly cover is where clauses. So we saw before restricting how a function behaves by having conditions on the types of the functions in the function's body. But another way to do this is actually to use a where clause, which happens before the function body is resolved and basically is used to determine whether a particular function candidate is useful. It should be used when picking overloads. So in this case, I wrote a procedure foo, which is just the same foo that we've seen before that adds two numbers. But in this case, I used a constraint that asks that the two arguments are numeric types. So foo should work with like integers and real numbers, but it shouldn't work with strings, even though the plus operator is defined for strings. So like I mentioned earlier, where clauses are checked before we resolve a function's body. In fact, they are resolved when picking which overload of a function to call. So in this instance, I have two functions, bar, one of which is called one of which is supposed to be called when x.type is a string, and the other one is when x.type is not a string. And this is unambiguous because when you call bar with a string, the where clause of the second function resolves to false because a string does equal to a string, so string not equal to string is false. And this candidate gets discarded. So only the first one is considered, and therefore this call picks candidate one. Meanwhile, for 1, 2, 3, 4, the where clause of the first candidate gets resolved to false because int is not equal to string, and therefore the second candidate is picked. Functions with where clauses are actually more specific and are preferred when possible. So this program is also unambiguous, even though I've removed the second where clause on the function bar that required x not to be a string. Basically, in the first case, when we call bar hello, the first where clause resolves to true because the string is equal to a string. And even though the second candidate matches as well because it has no constraint, it doesn't have a where clause, whereas this function does, so it's considered more specific. Meanwhile, in the 1, 2, 3, 4 case, the first candidate is rejected because integer is not a string, and the second candidate is taken instead. Okay, so now we've seen generic functions that have the types of arguments determined at compile time. And we've seen how these types are propagated through copies of the functions. And you can kind of think of this as basically substituting the argument types throughout the body of the function as appropriate. And we've also seen how they're resolved step by step in a way that's sensitive to returns and compile time conditions. But all we've done is substitute in types and, substitute in types. But with params, which parameters for short, I guess, we can also do this kind of compile time substitution with values that are known at compile time. This is kind of similar to const expr in C++, though I would say far more ergonomic and consistent. So we shall once again return to our param, to our foo function, but this time we'll have two arguments that are param instead of just arbitrary x and y. And params basically are required to have a value at compile time. So they have to be things that are known to the compiler when the program is being compiled or resolved. And we can still consider calls to like 1.02 and 3.2 because 1.0, 2, 3, and 2 are all literals that are known to the compiler because they clearly have an obvious and precise value. And when we call this, we end up with two instantiations. Once again, here I've written things in square brackets that aren't actually real Chapel notation, but they include information the compiler knows at this point. So when we call the function with 1.0 and 2, we end up with an instantiation in which x is a real number whose value is 1.0, and y, which is an integer whose value is 2. And immediately in the body, we perform a substitution to get 1.0 plus 2. The same thing happens with the second instantiation, where x gets instantiated with the integer 3, and y gets instantiated with the integer 2, and the body gets replaced with 3 plus 2. I'm drawing extra attention to the fact that, unlike the previous pieces of code, we've literally had these values get inlined into the body definition, into the function's definition. Because these functions return by param, they will actually return that exact value to the compiler. So this one will return 3.0-ish, modulo floating point arithmetic, and this will return 3.2, which 3 plus 2, which is 5. And so when you can think of calls to functions that have param return intent like this, as basically being replaced at compile time with their value. So because return 1.0 plus 2 returns 3.0, roughly, modulo floating point arithmetic, the call foo param 1.02 will pretty much get replaced with 3.0 directly at compile time. And you can do this with any of the following types. So ints, uints, and real numbers we've just seen. Well, we've seen ints and reals, but uints as well. Strings can be params as well, as can enums. And you might have encountered params if you've done some programming in Chapel, or encounter things that are actually params that you might not have known are params. So lists, sets, and data structures have basically two families, ones that are safe to use in parallel and are a bit slower, and ones that aren't safe to use in parallel but are a bit faster. This is controlled by a parseSafe argument to their type instructor, which is a param. So it's an argument known by the compiler at compile time, and it specializes the behavior of the data structure. If you pass in some compiler globals while compiling a program using the -s argument, which you might do if you're debugging the data parallel portions of your code, like parallel iterators. This might be covered in one of the performance demonstrations that I've mentioned earlier. Then what you're actually doing is providing a param value for some variable in the Chapel compiler code. Moreover, ranges have their bound kind and actually other properties described by a param enum. So if you do, one ... which is only a low bounded range, .bounds, you will get a param enum bounds kind .low. And this is known at compile time, so you can actually specialize your functions at compile time using this information. And finally, I mentioned earlier that conditions are removed at compile time if their condition is known at compile time. And that, in fact, is exactly when its condition is a param. So if return some param true is a param function that produces a param true, then this will get replaced with foo. And many of these things will be used when writing our own parallel iterators, though arguably this use of these features is a bit more incidental. In fact, taken straight from the parallel iterators primer, the count parallel iterator has a param argument tag of a param called iterKind, and a where clause that says, hey, this is an implementation of a standalone parallel iterator because the where clause says the tag must be a standalone iterator. I'll be giving this demo later today. Here's the QR code that links to the, I believe the GitHub repository for this. I hope the GitHub repository for this. And if not, the program that's giving the time for this demonstration. So in summary, many of Chapel's features use generic functions and types as part of their implementations, and this includes iterators, serializers, and many standard data structures. And understanding generics in Chapel can help you write more powerful code and also understand the standard code better, including reading its documentation. And we've seen that Chapel's generics are statically typed and stamped out by the compiler, so copied by the compiler, depending on combinations of argument types. We've seen that they support compile time simplification of type and param expressions to eliminate unused code, including code that would otherwise potentially produce errors. And they allow types of formals in functions to depend on preceding formals. This is the matching example, or three matching values example we saw. And finally, we saw how to use where clauses to provide more specific and constrained implementations of functions. And I believe that this actually concludes my presentation. So I'll pause now in case there's any follow-up questions, even though it looks like, despite having a few extra minutes, I am just finishing in time for the slot.
Awesome. Thanks, Daniel. I'll stop the recording and we can take some questions.